The last special Newton's second law problem that we're going to talk about is called the equilibrium problem. So we have a block of weight W is suspended from a rope tied to two other ropes at point O. One rope is horizontally attached to a wall and the other is fastened to the ceiling. The angle between the ceiling and the rope is 60 degrees. Assume the weights of the ropes and the knot are negligible. If the weight of the block is 100 newtons, what is the tension in each of the ropes? Now, for these type of problems, there's a couple things that you need to do. First and foremost, just like we do with problems at an angle or incline problems, we have to split that tension 1 up into x and y components. So let's do that first, all right? So I have my tension 1 up like this. They give us this angle right here is 60 degrees. All right, and this is tension 1. Now we're going to split this up into x and y components and then just leave them in components of T1 or in terms of T1. Okay, so this is my y component, that is my x component, T1y, T1x. So T1x will be T1 times the cosine of 60. T1y will be T1 times the sine of 60. Now, the next part of this problem is we need to draw a free body diagram of two things here. I know that there's only really one object, but since we have this point O as well, in problems like this, we're actually going to draw a free body diagram at that point as well. So we'll draw a free body diagram of this block, and we'll draw a free body diagram at point O, all right, pretending almost like there's something there. So first and foremost, free body diagram of the block. Here's my block. We have the weight downward, so force of gravity, which is just weight. And then we have the tension force up, and that is T3. All right. So we can already see what T3 is because we know that the weight of the block is 100 newtons. Now, that's the other part of this problem, is that because we're at equilibrium, what that means is that everything is at rest. We're suspended. So that means forces are balanced. So since we're at rest, the net force is equal to 0 because we're at rest, we're not accelerating at all. And so here, what that tells us is that T3 is equal to the weight, which is that 100 newtons. All right, so we already have our first tension. Now the second step to this problem, or I guess this is like step number 5, right, is to draw a free body diagram at that point O. And then we've already split up our T1 vector into x and y components, so now I'm going to draw them split up into x and y components. So we get the point O, we have our T3 down, we have T1y up, we have T2, nope, not T2, T1x, 1x to the side like that, and then we have T2 back, and it's horizontal, right, pointed to that wall right there. All right, so now this is our new free body diagram. Now we can already see that we can solve now for T1y, or T1, because we know what T3 is. Since T3 is equal to 100 newtons, and again, forces are balanced, that means T1y equals 100 newtons. So we know that T1y is that T1 times the sine of 60. We can then set that equal to 100 newtons. So T1 times the sine of 60 is equal to 100 newtons. So that tells us T1 is going to be equal to 100 newtons divided by the sine of 60. So T1 divided by sine of 60, 100 divided by sine of 60, we end up getting 115.47 newtons. All right, so that's my T1, and I have T3 already as well. And then now that we've done that vertical direction, we now need to look at the horizontal direction. So again, forces are balanced because we're at equilibrium, which means we're at rest, which means that T1x is equal to T2. So T1x, remember up here we got an equation for that. It's T1 times the cosine of 60. So we get T1 times the cosine of 60. We already know what T1 is, so now we can plug that in for T1 and we can get our answer for T2. So tension in rope 2 is equal to T1, which is 115.47 newtons, times the cosine of 60. and we end up getting that T2 is equal to, so I already have it in my calculator, so times the cosine of 60, we get T2 is 57.74 newtons. And those are the tensions in all of the ropes involved in this equilibrium problem.